Hello guys, welcome back to MedZone African Motives. Still working on engineering science N4. So in this platform, we shall be focusing on the angular motion. So basically, we've got some of the questions that we are going to consider later on. So we're just going to have an introduction, then we check at the application of these questions. How do they ask these typical questions? As we can see. So on the angular motion part, I'm just going to have a basic introduction of what we actually need to understand pertaining our syllabus. What is it that we actually need? So we have got angular motion in this case. So dealing with angular motion, this is actually taken from our linear motion, the one that we worked with on our N3, whereby we're talking of velocity, the final velocity, the initial velocity, the acceleration, the time, and so forth. But now we are no longer having the normal velocity that we use. Now we are now having the angular velocity. All right. So getting this from the normal circle, let us just have where we got this from its beginning. If we are given a presentation from our circle, let's say we have got a circle which is taken in this case, piece of a circle that we have, which is an arc. So from this arc that we are given, from this point up to this point of the arc, this is our arc here. That is the distance being taken, but now we are referring this as the displacement. So let's say we put A and B, and this being our S. So let me just put this way, from this point A to B being our displacement in this case, and we've got angle theta. All right, our angle theta is supposed to be in radians, always supposed to be in radians in this case. All right, so if we are to take this into consideration, we are going to find that according to this radius from A to B, this is our center O. So we need to say here, we have got the radius of the circle. So it follows that S, which is our displacement, which is the arc length. Remember, how do you calculate the arc length from your mathematics N2? We say the arc length is equal to the radius times the angle theta, provided that this theta is measured in radians. Provided that our theta is measured in radians, the arc length, which is our S, which is the displacement in this case, is equal to r theta. All right, so from this formula, it means we can even manipulate whatever that we want. So you can use the small letter for the radius, like S is equal to r theta. It's one and the same thing, meaning to say you can find your display, this theta, which is the angle that we are given in this case, which is now our angular. This one is just a normal displacement, but this theta is now our angular displacement. So this one is our angular displacement in this case. So we have got angular displacement, and this being our linear, we've got linear displacement, just like linear velocity. This will be our linear displacement, and this being the radius of the circle. But this theta, which is our angular displacement, is the angle that we are talking about, but being measured in radians. That is what I'm simply saying. So it follows that we can make theta the subject, where theta will be equal to S divided by R, so it will be S over R. So it means theta can be calculated from the displacement, which is our linear displacement over the radius, and this is going to give us our theta. We say this is the angle measured in radians, so our theta will be in rads. And also take note, for a complete revolution, if you refer to a complete revolution, we are going to see that one revolution follows that. In a complete revolution, we know this is equal to 360 degrees. But in terms of radians, this will be equal to 2 pi radians. So we are saying a revolution is equal to 2 pi radians in this case. We are referring from a revolution to the radians, which is the angle that is taken for that complete revolution to be taken. All right. So that is the first introduction part that you need to know, or that you need to understand from this angular motion. Then we go to them, just like when we talk of velocity, we say velocity is the change of displacement. It is the same thing. Here we are going to be talking of velocity, but it will be referred to as the angular velocity. We no longer we have the linear velocity concept. We'll be talking of the angular velocity, which is given as omega in this case. All right, whereby omega, if this is velocity, as we know, velocity is displacement over time. So it will be angular displacement over time. So we are simply saying in this case, omega is equal to the change of displacement over the change in time, which simply means we are talking of displacement over time. Remember, displacement is measured in rad, so it is going to be rad per second. So our angular velocity is measured in rad per second in this case, all right, which is simply the change of what? The change of angular velocity. So you can even make theta the subject, which is our angular displacement. You can make time the subject depending with what you want to calculate, all right. Also, we talked of linear acceleration in our linear motion. Now we are going to be talking about the angular acceleration. So we are going to have the angular acceleration in this case. All right, so this is now angular acceleration, which is referred as alpha. So the angular acceleration, just like acceleration from our linear motion, we know that acceleration is equal to velocity over time. So it is the same concept with our angular acceleration. It is still the same. So angular acceleration is going to be the velocity, which is our angular velocity, which is omega. So it is going to be omega over time. That is the angular velocity over time, which is simply the change in velocity, the change in angular velocity. So if we are given now, just like velocity, we know that the change in velocity can be given as v minus u over t like this, whereby you are given final velocity and initial velocity. It is the same thing also for angular acceleration. We can have the final angular velocity, which is omega 2 minus omega 1. This is over time. I shall talk about this omega. What is it that we are actually talking about? We just said it's omega, this one. And the units there, it is going to be rad per square second. In this case, we are referring rad per square second. All right. So let me talk about this omega that we are saying is our angular velocity. What is it that we are referring to here? The omega is simply taken from from the revs per second. If we are given, let's say our speed, we might be given speed. Okay, let me elaborate by writing when given so that it can make sense. So let us just have it aside here. So I'm saying from this omega, this one, all right? When we are given a condition in a revs per second, so when given speed, when given speed in revs per second, remember our speed in revs per second, that will be n. So we can actually calculate our omega from there, from the speed. Our omega is going to be given as 2 pi n like this, when it is given in revs per second. But when it is given in revs per minute, all right, when given in revs per minute, I'm just going to represent as the capital letter N for revs per minute. I'm going to use the capital N. For revs per second, I used small letter n. So here I'm going to use capital letter N for revs per minute in this case. Our omega is going to be 2 pi n over 60 now. That is what we are going to have. We are going to have 2 pi n over 60. So if we are to consider this now to say omega can be given as n as 2 pi n like this, it means we can even calculate our angular acceleration. Please here be very, very careful on this part. We can calculate the same angular acceleration, this one, in terms of n, in terms of omega being given from the speed. All right, so I'm saying when given the speed in revs per second, meaning to say our angular velocity in this case is going to be given as, all right, our angular acceleration, I mean, is going to be given as, instead of writing omega 2 like this, our omega 2 is going to be 2 pi. And remember, you'll be given two speeds, which are in revs per second, n1 and n2. So it is going to be 2 pi n2 minus 2 pi n1 like this. All right, 2 pi n2 over the time now. this is already in revs per second. So you're going to simply divide by the time. But if you check here, because this is common, 2 pi is common, we can factor out the 2 pi. So at the end, this is going to be given from this. We can have this formula as to factor out 2 pi. You are going to remain with n2 minus n1, everything over the time in seconds. So you're going to obtain the angular acceleration again in rad per second. So it's very, very important. This formula, you can use it direct. Instead of converting to find, you can use this formula direct as it is. You can use this formula direct as it is. That is when you are given what? The speed in revs per second. All right. If you are given your speed in revs per minute now from n, which is in revs per minute, you are given your speed in revs per minute. It means we are going to have the same formula, but now we have to divide by 60. Remember, I said there, you divide by 60. So therefore, our angular acceleration is going to be given as 2 pi n2 minus n1 over 60t, like this, having our answer again in rad per square second. So these are the formulas that are very, very important. So this is in revs per second, but this is now in revs per minute, this one revs per minute. When you are given your speeds in revs per minute, these are the formulas that you can alter to use instead of converting to use this formula, because this one is the basic formula. This is the basic formula that you're supposed to use. But instead of altering now to calculate omega-1, you can simply substitute these values direct on your formulas like this. All right. So these are the basic formulas that we need. Then in addition, let me add this in addition before we look into our questions. All right, or I can even write it down here. So let me just add in addition of this before we check our questions. So in addition, I want you to also understand that we talked about the theta. Remember, from our linear motion, S is equal to the average velocity U plus V over 2 times time. So, and I said this is now taken as angular motion. Instead of writing S, it's now theta in angular motion. So theta is equal to U1, which is represented by omega-1, final velocity, which is now omega-2. So we are going to have this formula as omega-1 plus omega-2 over 2 like this times the time. So this is another formula that we can use to calculate our angular displacement in rad per second. Remember, this represents what? Your angular displacement. This is your angular displacement. Let me just have it here. So here we are talking about the angular displacement in this case. All right, so that's angular displacement. And here we are talking about our angular velocity. So this is now our angular velocity. But omega-1 simply means this is our initial, final, just like U and V, initial velocity, final velocity. So it's initial angular velocity. All right, so that is when the speed now is given in revs per minute. All right, when we are given speed in revs per minute, when given speed in revs per second. I said whenever you're dealing with revs per second, it's best for us to use this as what? As n, our speed in revs per second. We are going to see that the theta here, remember omega-1 is given as 2 pi n. So meaning to say our theta now can be given as 2 pi into n1 plus n2, Remember, you factor out the 2 pi just like the previous case that we had over 2 times t like this. All right, so this is the formula that you guess you can cancel 2 and 2 this part if you want, but this is the formula that you can now use. Instead of converting to omega, you can simply use this formula when you are given your speed in what? In revs per second. But when we are given this speed in revs per minute, all right, when given speed in revs per minute, and I said revs per minute, it's best for us to use capital letter N for speed. in revs per minute. So therefore, our theta now, which is our angular displacement, is going to be given as 2 pi n1 plus n2, but you divide by 2, these 2 multiplied to 60. So it's going to be multiplied to 60. Remember, revs per minute, you have to divide by 60 to obtain per second. All right, that is multiplied to the time. So all these formulas that we are talking about, they can give us the exact value of the angular displacement measured in radians, just like what we saw on the previous case, where I said we can use n in place of the angular acceleration that we are used to from this formula. We can calculate using n, which is allowed. You can actually do that direct, which is the same thing. If you know that displacement, it's average velocity times time, you can find your average velocity, which is angular velocity, using also the speed in revs per minute or revs per revs per second or revs per minute. All right, so that is what we are going to have. Then lastly, I think now we've got a lot of formulas which are important. Now, lastly, from our linear motion, I'm going to convert those formulas that we used to talk about. Remember, we had formulas from our linear motion. All right, or let me write the linear motion this side so that it can make sense. I just want us to convert those formulas that we know from our linear motion, from our N3 engineering science. Remember, we talked about the linear motion concept. We want to convert those formulas now to angular motion. It's just one and the same relationship. Remember, we had got formulas such as S is equal to, the first one that we just talked about, S is equal to U plus V over 2 times time. That is, we are talking about the displacement, initial velocity, final velocity time. So here we are no longer having S, we are now talking about theta for angular displacement. So angular displacement is equal to the initial angular plus the final angular over 2 times the time, which is the angular velocity. All right. Also, we have got formulas such as V is equal to U plus AT, whereby V is the final velocity. Here, our final is omega 2. So omega 2 is equal to the initial, which is omega 1, plus the acceleration under angular motion is alpha angular acceleration, like this. T is the only part that does not change. All right, we have also formulas such as S is equal to, remember, it's UT plus half AT squared. There's a formula like this under linear motion. Remember, our S angular displacement now is theta, but here it's linear displacement, is just displacement. Now it's going to be given as theta. So theta is equal to UT, which is initial angular now, which is omega 1. So it is going to be omega 1 times time plus half of, this is acceleration. So it's going to be angular acceleration T squared. So the same formulas that we had, remember also on our linear motion, we've got the formula V squared is equal to U squared plus 2AS. All right, that was plus 2AS plus 2AS, like this, whereby this is the final velocity, which is now omega 2. So we are simply saying omega 2 squared is equal to initial, which is omega 1 squared plus 2AS, A being the angular acceleration now. S, remember, S is now given as theta. So this is what you simply need from these formulas. So in we can simply have this as in basic form. In basic form, we can have this as omega 1. This is our initial angular velocity. Initial angular velocity, which is measured in rad per second. All right. Omega 2, that is our final angular velocity. Final angular velocity measured in rad per second. Then we have got theta. Our theta in this case is the angular displacement. We talked about this. This is our angular displacement, which is measured in rads. Then we have got alpha. alpha representing the angular acceleration. So this is our angular acceleration, which is measured in rad per square seconds. And we also have t. So t does not change. This is still our time, and our time is measured in seconds in this case, which is just s like that in seconds. So that is this is the other part that you need to understand. So the other part that you're gonna have is just for the relationship. Maybe we can just write it here, then we conclude everything. So they'll also want you to know the relationship between the, remember I talked about linear and angular motion. So we are going to have the relationship in this case. That is the relationship between linear and angular motion. So we've got the relationship between linear and angular motion. What you need to do is to understand, remember in linear motion, that is where we are talking about the velocities, the linear velocities, those initial and final, this u, and the acceleration, where we talk about s and so forth. All right. So now we want to convert these to the angular motion, whereby we are now talking about theta, omega, and the angular acceleration there. So what is the relationship between these two? That is what we need. So if you are going to check that, we can have this as, let us start with the velocity. Velocity is equal to everything that is in angular motion. If you multiply it by the radius, it is going to give us the value for the linear, everything in angular motion. So it is going to be r times omega. So the moment you multiply omega to the radius, it gives us what? The velocity. The same thing with acceleration. You multiply it to the angular acceleration. The angular acceleration, when we multiply it by the radius, it gives you the acceleration, which is for the linear. Also, s is equal to r theta. If you multiply the angular displacement by the radius, you obtain the linear part. So this is with this conversion, you can even change like this one. You can divide by radius, meaning to say omega is equal to d over the radius in rad per second. Also alpha here, alpha is equal to a over the radius in rad per square second. Also theta is equal to s over r in rad. So it's a play around that you are simply making from this information. All right, so let us rush to the question. I think I have explained everything that you actually need before attempting these questions. All right, I hope we've got our question on this side here. We have these other formulas here. So there we are. We are given the question number 2 in this case, whereby we're given that the effective diameter of on the thread of a cutter is 405 millimeters. All right. So there we are given the diameter in this case. All right, let us just take our information. We do not know what's going to happen in this case. So we are given the diameter being 405 millimeters, of which we can change this diameter to meters. All right, change to meters, just multiply milli means times 10 to the exponent of -3. So that is going to give us 0, so we are going to have 0,405 in meters. All right, your units in meters. So the question is on 2.1. Calculate the following 2.1. The distance that a point on the thread, take note, the distance that a point on the thread of the tire will cover if it does 1 revolution. If it does 1 revolution, that was the part that I was explaining from the beginning to say, if you are dealing with a movement that is happening on an angular, a revolution is taken as 2 pi radians. That is a complete revolution. The whole revolution is taken as what? As 2 pi radians. So which is the 2 pi radians represent the angular displacement. That's your theta. So meaning to say a complete revolution, our theta is going to be 2 pi radians, which I said in degrees this is equal to 360 degrees. So the person here is asking us the distance. So what this person is simply asking us guys here is, do we know the conversion, which is the last part that we talked about, the conversion between the angular and the linear, because this distance is linear. This one is a linear once they say distance, but this theta is angular. So you are converting from angular to the linear because we have got the diameter in this case. So we're going to use the concept. Remember what I said? I said S is equal to R theta. Anything that is in angular motion, if you multiply it by the radius, it gives you the linear motion, which is the distance now. So that means in this case, we're simply going to multiply from the last formulas that we did in this case. That was the percent in this case here. So that means our S is going to be the radius. Remember, radius is diameter over 2. So that would be 0.405 over 2 times the theta in radians. A complete revolution, we are given a complete revolution. So our theta is going to be 2 pi. All right, so that's we obtain our distance in the meters in this case. So this was going to give us something like 1,272 in meters. All right, so that was the idea of the question. Then 2.2, we are now asked the angular displacement of the point on the thread of the tire after 10 revolutions. After 10 revolutions, the angular displacement, of which I said theta represents the angular displacement. So on one revolution, theta is equal to 2 pi. So what about after 10 revolutions? You simply have to multiply. All right, so this one was a direct person. So they are saying, we are saying in a complete revolution, theta is equal to 2 pi radians, which is theta represents the angular displacement. So if theta represents the angular displacement and you are given that after 10 revolutions, how many revolutions are we having when theta is equal to 2 pi? This is on a complete revolution, one revolution. So if there are 10, we are simply going to multiply. So our theta is going to be 2 pi times the 10 revolutions. Now, remember, a complete revolution is 2 pi. So what about 10 of them? So we are going to have 20 pi at the end in radians. Remember, I said angular displacement is measured in radians, all right? So that is going to be 20 pi rad. If you want, you can write it as a decimal. That is theta is equal to 62,832 in rad. All right, so that was it in this case. Then 2.3. Let's see 2.3. The angular velocity of a point, take note on the thread of a tire when the car is traveling at. So you need to understand, we need the angular velocity. All right, let us take our information. That's 2.3. So here we've got 2.3. So at 2.3, we need to calculate the angular velocity. We do not know our angular velocity in rad per second. All right, but what we know is that we are given that it's taken from the point on the thread of the tire. When it is traveling at this distance, at this speed, which is 100 kilometers per hour. So what are we given there? We are given the velocity from linear motion, which is 100 kilometers per hour. So the question here is simply convert from kilometers per hour from linear motion, convert to angular motion. That is the type of the question they are asking here. So you go back to that relationship that I said, everything that is in angular motion, once it is multiplied by the radius, it goes back to linear motion. So meaning to say, us here, we want to calculate in angular motion. So we have to divide now by the radius so that we find our omega in this case. So meaning to say, our omega in this case here is going to be given as, all right, so let us divide. If we divide here, we are going to have omega as the velocity over the radius measured in rad per second. Since this is rad per second, this B must be in meters per second. So you're supposed to convert the velocity, this one, to meters per second. So how do we convert to meters per second? We are given a velocity of 100 kilometers per hour. So remember, we multiply by 3,6. So if multiply by 3,6, because 1 meter per second is equal to 3,6 kilometers per hour. So you're going to multiply by 3, divide actually, because this is in kilometers per hour. Sorry for this. You see, this is right to write the formulas. So here you're supposed to divide, because this is 100 kilometers per hour this side. You want the answer in meters, so you divide these two. All right. So that's 100 divided by 3,6. All right. So this is going to give us a velocity of 27,778 in meters per second now. So with this velocity, I'm saying if you are to divide by the radius, because we saw that V is equal to R omega, as we want the omega, so you have to find the radius. Remember here we said radius is simply diameter over 2. So from this value, if you are to divide here, what is going to be the radius? Radius 0,405 divided by 2. So this will give us something like 0,2025 in meters. So this is our radius. All right. So we are going to divide, since we want the answer in rad per second. So we have to make this one the subject. So therefore, our omega is going to be V in meters per second. Our V in meters per second, 27,778 over the radius in meters. And our radius is the one that we calculated here. And our radius, we said, is what? 0,205. All right, so this is going to be 0,2025. All right, so there you obtain our omega, which is going to be 137,17 5 and so on, 5.3 and so on. So this will be in rad per second. So this person actually wanted you to know the conversion. If you check from the last part that I wrote on our conversion, that was all about this person. All right. So let us check the other part of the person now. Now they are saying the angular retardation of the vehicle. Take note, in this case, take note about this part of the question here. They are saying the angular retardation, take note about this part, the angular retardation, if the vehicle is brought to rest, it is brought to rest with the uniform reduction speed from 100 kilometers per hour in, take note, okay, let us be stage by stage. The angular retardation, meaning to say we need to calculate alpha here. If the car is brought to rest, so we are the moment, which means we're talking about our final angular velocity omega being at 0 rad per second. It's going to be at 0 rad per second. Final is brought to rest with the uniform reduction in the speed from, take note where we're coming from. The 100 kilometers per hour, the one that we used here, the one that we're working with at 2.3. Remember, at 2.3, we were working with 100 kilometers per hour, and we have the angular velocity there. So we have the angular velocity for this part from this speed, from which is our initial. So they are saying at 100, let us take our information. At 100 kilometers per hour, we got that our angular velocity was what? Was 100 and what? This one. This is the value that we are going to work with, this one. This is the value that we are going to work with of 137. So I want us to take this value into consideration. I'm going to remove this part, but I want us to have this value. All right. So with our value, I want us to write it here. So this is what they are saying. From the 100 kilometers per hour, we are having our omega 1, which was the speed that we calculated from our previous question. The omega that we calculated, remember our omega there, we said it was 137,175 in rad per second. All right, this is our initial. So we are asked to calculate the angular retardation, which is our angular acceleration, which is alpha. This is the one that we want. If the vehicle is brought to rest, meaning to say the final, which is our omega 2, it's at 0 rad per second. At rest, there is no movement. So within the time frame, our time being at 25 seconds, what is our alpha, which is angular acceleration? Remember, on our formulas, I said the angular acceleration can be taken from the formula, the change in angular velocity over the time, whereby the change in angular velocity is the omega 2 minus omega 1. So this is going to be omega 2 minus omega 1 over the time, whereby I was saying if you are given these speeds in revs per second, that's where you use the 2 pi n1 and 2 pi n2, but yet it's already in rad per second, so there's no converting or any other important formula. This is the formula, the change in angular velocity over the change in time. All right, so you're going to substitute here omega 2, this is at final 0, minus omega 1, which is our angular velocity, the one that corresponds at 100 kilometers per hour, which is 137,175 over the time, and our time there is 25. All right, so that means we are going to obtain something like negative 5,487 in rad per square second. All right, so this is going to be in rad per square second. So be very careful how this information is given. All right, so that was the first part of our questions that I had made for you. Let us check the other part here and see. So here we are asked to define angular acceleration. So as we have been talking about angular acceleration, it simply means the rate of change of angular velocity. So this one is the rate of change of angular, the rate of change of angular velocity. So it's gonna be of angular velocity. And remember, this is measured in rad per square second. All right, so that's it. 2.2 we are given. This is now where we are given revs per minute. I think this one we are going to learn a lot from those formulas that I listed before. Here we are given that the spindle of a driving machine, we have got a spindle of a drilling machine here rotating at, slows down to, so it is rotating at this speed. This is the initial speed in revs per minute. So in revs per minute, I said it's best to use capital letter N for revs per minute. So we have given the initial speed of 1,500 revs per minute. It is slowing down, that is there's a retardation to a speed of 600 revs per minute in this case, to this speed of 600 revs, while making, take note, while making 48 revolutions. What is it that is hidden? What is it that is hidden from the 48 revolutions? What is it that is hidden here? Remember, I said from a complete revolution, we have got 2 pi radians. And what does 2 pi radians mean? It means we are talking about the angular displacement from there. So in this case, they are hiding the angular displacement by writing 48 revolutions. You are supposed to know that if it makes 48 revolutions, therefore the total speed, the total displacement is going to be what? For 48 revolutions, you are going to multiply by 48. So it's going to be 48 times 2 pi, which is going to give us 96 pi radians. This being the theta, the angular displacement, it's theta. So we are given the value for theta also, which is 96 pi in radians. So take note, guys, how do they give information? So the question is, let us see our question. Calculate the following: the angular retardation of the drilling machine in rad per square second, the angular retardation, which is our alpha. Remember, on those formulas that we talked about, we said if you are given the speed in revs per minute, our alpha in actual sense, our alpha was supposed to be given as the change in omega, which is omega 2 minus omega 1 over t. But since we are given this, we are, in fact, the time, we do not have the time in actual sense here. We do not have the time. So where are we going to obtain our time? Where are we going to obtain our time? So it means this formula is limited. All right, our formula is actually limited. So where are we going to have our time if we do not have this? So this formula, and they are asking the time on the second place here. So it means our formula this time is limited. We can't use this. All right, our formula this time is limited. As you can see, item 2, that's where they are asking the time. So we have to think along our formulas. Okay, remember, we are given N1, meaning to say it's like we are given omega 1 and we are given omega 2. And there are those formulas that we listed, like theta is equal to omega 1 plus omega 2 over 2 times time. If you still remember those formulas, we want to take from those list of formulas, but the one that carries what we have in this case, which is what? Omega. So remember, we have got omega 2 squared is equal to omega 1 squared plus 2 alpha s from those formulas that we listed, which is taken from v squared is equal to u squared plus 2as. All right, so this will be theta 2s 2 alpha theta. Sorry, pardon for me, this guys, 2 alpha theta, was now we are in angular motion. So we can make our alpha the subject in this case. All right, we're gonna make this one the subject. All right, so let us find alpha to be the subject, because this is the one that we want angular. So we are going to transpose to be omega 2 squared minus omega 1 squared. We divide by 2 theta in this case. So divide by 2 theta is equal to alpha, like this. So this is what we are going to get from this formula, meaning to say we can calculate our alpha from this formula, omega 2 squared minus omega 1 squared over 2 theta. All right, so if we can check now on the substitution part, if you are to check there, it's going to be difficult for us to work with these speeds. All right, there it's going to be difficult because we are squaring our values there. So it's going to be very, very difficult. So we do not have option. Let us convert our values to rad per second. Remember, our omega is supposed to be rad per second, and I said omega is equal to 2 pi n over 60 if you are given your speed in revs per minute. So if it is omega 1, this is going to be n1. So our omega 1 is going to be 2 pi times n1, our n1, which is 1,500 over 60. So we are going to obtain our omega 1 in this case, which is going to be 50 pi. So this one is going to give us 50 pi rad per second. We move on to omega 2 in this case, the final velocity, the final angular velocity, which is going to be 2 pi times n2. This time we are going to use n2, which is 600 over 60. So that is going to be omega 2 is equal to 20 pi. So we are going to obtain 20 pi in rad per second. All right, we have omega 2, we have omega 1. Now we can calculate our angular acceleration. So take note, sometimes your formulas might be limited, and you have to, that's why you have to start your formulas from your N3 part. All right, so therefore our alpha here was going to be omega 2, which is 20 pi squared minus omega 1. Our omega 1 is 50 pi, so it's going to be 50 pi squared, everything over 2 times our theta. Remember, our theta, our angular displacement, is the one that I calculated. I said it was hidden from the 48 revolutions. You get your theta in radians, and your theta in radians is going to be 96 pi. So here we are going to multiply to 96 pi in this case. All right, so that's it. We have got our angular retardation in which is going to be a negative. So that's negative 34,36116 and so forth, which is going to be 361 in rad per square second. So the negative is actually showing us that that's an angular retardation. So you can even leave that negative on your final answer, which is not even a fact, which is not even a problem. All right. Then the item 2 now was the one that where they are saying the time taken to slow down. All right, now we can calculate our time since we have got this alpha. Okay, let us choose which formula can we use in this case from these ones that from what we have. Remember, we have got omega 2, we have got omega 1, we have got alpha, and the one time. So we can simply use that formula that we said, if you still remember on our formula, as I said, omega 2 is equal to omega 1 plus alpha t, which is taken from our linear motion. In linear motion, we say v is equal to u plus at, but now it's omega 2, final angular velocity, initial angular plus alpha t. So we want time in this case, so we can make t the subject. We're gonna take this side. So we are going to have this as omega 2 minus omega 1 divided to alpha in this case. This is going to give us the value of time. Okay, so you're going to remain with alpha t, you divide by alpha in this case. And we have all these values, so meaning to say we are going to obtain our time. So therefore, our time is going to be omega 2. Remember omega 2 there, that's 20 pi minus omega 1. Our omega 1 in this case is 50 pi. Everything over the angular acceleration, the angular retardation, I mean the one that we got as negative 34,361. All right, so this is going to give us the time that was taken for this object to slow down. All right, so this was actually a stretching type of a question. It stretches you. All right, 2.7 28 and so on, which is 2.743 seconds. All right. So this question, it was actually a stretching type of a question. It stretches you to think along the lines of your formulas, go back to your linear motion, and relate to from linear motion to angular motion. But it's not that much. It's not that much. All we need, guys, is to work with more questions and revise your formulas. Manipulate your formulas. Do not just use the formulas that you are given. Learn to manipulate a formula to the favor of the question that you are given. And with the information that you are given actually is the one that relates, that tells you the formula, which formula to use. You might be having your own formula, say, I want, but when you are limited to a certain information, you have to use that information that you are given. So that is all about engineering science. You need to know how to manipulate the formulas or to work with certain formulas. All right, guys, that's it for now. From Maison African Motives, working on engineering science and for till we meet again.